we have to target all emissions to solve this problem of climate change. And super high tech engineering solutions are really important, and they're part of the portfolio of solutions that we're going to need. But solutions that are a little more simple have more potential to be implemented fast, and we need solutions fast for these problems.
Welcome to Growing Impact, a podcast by the Institutes of Energy and the Environment at Penn State. Growing Impact explores cutting-edge projects of researchers and scientists who are solving some of the world's most challenging energy and environmental issues. Each project has been funded through an innovative seed grant program that is facilitated through IEE. I'm your host, Kevin Slyman. On this episode of Growing Impact, I speak with Juliana Vasco Correa, an assistant professor of agricultural and biological engineering at Penn State. Our conversation looks at her project titled Methane Emissions Mitigation and Carbon Capture with Biofiltration. What do you do when the traditional method of eliminating methane, flaring, does not work? For air streams that have a low percentage of methane, such as emissions from dairy barns, there needs to be another solution. Juliana describes how she and her colleagues are designing and building biofilters that can convert methane into carbon dioxide and then capture that CO2.
Thank you for being here and welcome to Growing Impact, Juliana.
Thank you very much, Kevin, for inviting me. Happy to be here.
Can you just provide an overview of the project and give us just a flavor of what it is that you're working on?
Yes, absolutely. So what we're trying to develop is biofilters for air streams that have methane. So methane is a greenhouse gas that is very potent. So what we're trying to do is to use these biofilters that are like these big columns packed with a support material and that have bacteria on it.
Okay.
And the bacteria are able to mitigate this methane, to basically eat the methane that is in the air and reduce the impact.
Let's discuss methane. So where is methane primarily coming from and how is it damaging?
Yes, well, methane is actually the second largest contributor to climate change after carbon dioxide. And it comes mainly from what we call enteric emissions. So emissions from ruminants, from mostly cows and other animals like that. Mm-hmm. That produce it in their stomachs because they have bacteria on it. So they have these certain bacteria that ferment the feed inside their stomach and produces methane. Mm-hmm. So that's the main source. But actually, even though it's the main source, it's only about 17% of the total methane emissions. And that's the key with methane, that it is very distributed. So it also comes from dams, from rice paddies, from leaks in pipelines, from coal mining. Mm-hmm. So it's very, very distributed, and it's very diluted. So most of the airstreams that are around that have methane have a very low concentration of methane. So actually capturing and doing something productive with it is very difficult. So if the methane, for example, is in a concentration higher than 5%, we could just burn it. We could just flare it. And if we flare it, it's not an ideal solution, but it converts it from methane into carbon dioxide, which everyone will think, well, that's not good. Carbon dioxide is not good. But actually, methane has a global warming potential of about 36 times more than carbon dioxide.
Okay.
So it's way worse for the environment. So if we convert it into carbon dioxide, we're able to reduce the impact in global warming by more than 30 times. So flared works. The problem is the most airstreams with methane have less than 5% methane concentration. And if it's that diluted, then it just doesn't burn. So we cannot flare it. So those are the streams that we're targeting, the ones that are very diluted, very distributed, and then we're thinking, well, those we can fix them with the biofiltration.
All right. And so we can't flare the methane that's coming out of cows, on my guesses, right?
Exactly.
The cows would probably not appreciate that.
They will not, but of course, we will not go directly to the cow, but take the air, like for example, out of a barn in a dairy
Right.
farm. But that, if we try to flare it, it will not flare. It's it's less than 1% usually.
Oh, interesting. Okay.
Mm-hmm.
So even though cows account for a large amount, it's still it would still be such a diluted amount.
Yes.
That it would not work. Okay. Are there other emissions that this project is focusing on? Are there any others that you're looking at?
Yes, so precisely CO2. So what we're trying to do with these biofilters is something very similar to what will happen in the flaring. It's convert the methane into CO2. But instead of doing it by combustion, like in the flare, because it just doesn't happen, the bacteria do it. So the bacteria are able to eat the methane and then they produce carbon dioxide.
Let's actually talk about biofiltration and how it works.
Biofiltration, then what we're trying to do is to create these big biofilters. There will be like these columns that are packed with a material where the bacteria grows, but also that is able to capture the carbon dioxide. So we will take the air out of these places where there's the emissions, for example, a barn from a dairy farm, and then pass the air through the biofilter. And then the bacteria that is in there is a special kind of bacteria. We call them methanotrophs that are able to eat methane and produce CO2. And then hopefully this CO2 will get absorbed and captured inside the biofilter because of the material. So the material is something very common. It's a mixture of materials, mostly organic materials, compost, and we're gonna try some residues from the forestry industry, like sawdust, and then do some treatment to it so it can actually capture the carbon.
So when you look at your project, what are you hoping it will achieve?
Well, this 1-year project and this short term, what we're hoping is to develop a pilot system in the lab to be able to test some of our theories. So we are doing a lot of engineering design with our students, building the systems in the lab and building all the controls so we can test a lot of our theories. And we're also focusing on 2 goals of the engineering of the biofilter: the microbes and the material. So we're trying to engineer the microbial communities, the bacteria that is inside the filter. There will be several types, and we're trying to engineer them in a way that they're stable and they work together to achieve the maximum amount of methane oxidation or methane mitigation. So that is one goal. And the second one is the materials part that, as I said, is making these materials that are functional and are able to be a good support for the microbial communities, for the bacteria, but also capture carbon.
All right, this is exciting. It seems it's such a, and don't get me wrong, I'm sure the work behind the scenes in the lab and getting that all figured out. Don't get me wrong. I'm not trying to say that it's simple or, like, oh, of course, but it's such a simple concept, right? It's a filtration. We've been using filters, but this really cool idea of adding these microbes that can eat methane and maybe then the material can actually capture the carbon. Yeah. I mean, it's really cool.
I think if it's simple, it's more likely to work. So I find it as a compliment if you think it's simple. Plus, I do think for a solution like this, when we're talking about emissions that are quite diluted, that are, we have to target all emissions to solve this problem of climate change. And super high tech engineering solutions are really important and they're part of the portfolio of solutions that we're going to need. But solutions that are a little more simple have more potential to be implemented fast, and we need solutions fast for this problem. So I think that's how I see it. For a simple solution like this, yes.
Well, that's really that's well put. So I appreciate that perspective. All right. So you were talking about your lab and you're going to have students and others helping.
Yes.
Could you talk about how a project like this would benefit from, or does benefit from, an interdisciplinary team?
Yes, absolutely. We do have a fantastic interdisciplinary team and have been working on this project for some months now. I'm a bioprocess engineer, and that is the main goal of this project. So that's why I'm leading the team. But we also work with other two professors, Dr. Marianne Bruns, that is a soil microbiologist. So she's helping us in all the microbial part and try to figure out how to get the best microbial community composition in a natural way, not in a super sophisticated synthetic biology way, which would be great, but maybe not so stable, but in a more natural way, trying to use the natural systems and develop the microbial community out of what already exists in nature. And then Dr. Lauren Greenlee from chemical engineering, that is helping us with the functionalizing of the materials. So she knows a lot about these materials, and she had the idea of this carbon capture as part of the biofilter. So we've been working with a group of students from different disciplines, from biological engineering to biorenewable systems, and actually also a student from engineering design, helping us actually design and build the biofilter.
Do you have any next steps or future plans that you can talk about at this point?
Yes, we actually do. Okay. We've been thinking on another, and it's actually related to one of the questions you asked about other emissions. We've been thinking about the third main emission from greenhouse gases, that is nitrous oxide. So actually from the emissions from agriculture, nitrous oxide tends to be the most important one. So nitrous oxide is way more potent than even methane. It's about 300 times more potent in global warming potential than CO2. And the thing is, most people that have tried to study biofilters have not measured nitrous oxide at all. And what we think is there might be a risk that under some conditions in these biofilters, there might be production of nitrous oxide. And if that happens, all the benefits that we will have will just get eliminated, because even if we produce just a little bit of this gas, since it's so potent, it will be a big problem. But it also seems that there's the possibility that if there's a little bit of nitrous oxide coming in the stream going into the biofilter, like for example, coming from a barn, that it actually could be also mitigated. So we want our next step after we figured out the basis of these biofilters is to figure out more detailed dynamics of all these other greenhouse gases and when would they be produced for us to then try to avoid those conditions, and if we can mitigate those other additional greenhouse gases.
Juliana, thank you so much for coming on the podcast and sharing about your project.
Well, thank you very much for inviting me. It's a pleasure, and hopefully people are interested in our project, and if anyone wants to collaborate with us, we'll be happy to hear from you.
You've been listening to Growing Impact, a podcast by the Institutes of Energy and the Environment at Penn State. I've been your host, Kevin Slyman. This has been Season 2, Episode 5. Thank you for listening.